Okay, we should get started again if we want to finish anywhere near by 5. We looked so far today at really the definition and specification of a very little language. It was just numbers and booleans and not much else, right? And that's a little bit small, so we're going to now look at another language using the same sorts of techniques on how to define what it is. And we're going to look at the Lambda-Calculus. So who here has seen the Lambda-Calculus before, is familiar with it? Okay, a good amount of people. Who here has never seen the Lambda-Calculus before? And this will be the first time you're seeing it. Okay, a couple people. So this is something that was originally invented in the 1930s by Alonzo Church. And we kind of did things a bit out of order in that the Lambda-Calculus came way first, and everything we've seen so far has been developed after the fact with that in mind. So this is sort of the origin of all of these ideas on what programming is, how to define what it is with this mathematical view in mind. Okay, so let's just dig in and start going. So the Lambda-Calculus, it's a really small language, and it looks, it's very austere, and it looks like you can't do really that much with it. But it's a little bit deceptive, right? It's a small but mighty sort of thing. So let's first, right, we're going to follow the same plan. We're going to look at the syntax and then get into the semantics of this language. So what's the syntax of expressions E in the Lambda-Calculus? So this is for the Lambda-Calculus. What is the syntax of expressions E? There's only 3 cases. So surprisingly, it's a lot smaller than what we were dealing with that was already a very toy language. The 3 cases are a variable. We've seen those. Just a variable x. An application, E1, applied to E2. And this is typically written like this, as 2 terms or 2 expressions side by side with just juxtaposition or just a space. Very minimal syntax. And then where it gets its name from, a lambda abstraction, lambda x.e. All right? And so these are the only 3 things. And really, the Lambda-Calculus is just about specifying one construct, which is functions. Right? What do functions do in the most abstract way you could possibly think? And so this is the way the functions are written. It's a mapping from a variable to some result. That's right. So x here, I'm using the dot again. That's a bound variable. And e is the result if you were to somehow provide it with a parameter. And then this is the function application, where given some function E1, I want to apply it to the argument E2 to see what the result actually is for this application. And so this is the most typical syntax that you will see in every paper and textbook all over the place. Right, this is how people write down the Lambda-Calculus syntax. We can also write it in that more detailed and tree-oriented syntax just for comparison to see what it's like. So how would that look? So using trees, what does that look like? Same thing, different way of writing it. So E, right, we just wrote a variable expression as just the variable. An application, right, this is a syntax node with 2 subtrees. And there's a name for the node, which is something for application. So let's just call that app E1, semicolon E2, which is a syntax node of 2 subtrees. Right? And then lambda, I'll write as just lam And then x dot e, staying with that convention that x is a variable being bound in inside e by this syntax lambda node. And so we write x dot as that same thing. And that's where the dot convention came from, right? This was the old syntax, and we just kept using it over the years. OK. Was there a question? So this is the lambda calculus. That's it. All right. That seems pretty simple, right? That's not that much. And well, let's start saying a little bit more about what it is, right? So the lambda calculus isn't just a notation for writing things. If that's all it was, it'd be dreadfully boring, right? There's also some intended semantics for these things. And I'll start with the three primary laws, and we've kind of seen some of that already. And that was one of the questions. So the first one, the first law of the lambda calculus, is the alpha law, because alpha comes first in the Greek alphabet, right? So what is so these are the lambda calculus laws. Okay, lambda calculus laws. So the first one's going to be alpha. So what's the alpha law? Do we have a guess on what the alpha law is about based on the previous lectures? Yeah, alpha equivalence. So what's alpha equivalence about? Renaming, right? So this is where the idea of static binding and alpha equivalence came from, right? Is renaming in functions. And so what is the only binder of this language? There's really not that much to pick from, but it's the lambda. That's the only thing that really sets up a variable so that you can refer to it later. And so alpha equivalence says that the name on a lambda doesn't really matter. It's just for our own benefit to be able to match up the introduction and use of a variable. And so alpha law says that doesn't matter. You can always rename it, and it's the same thing. So that's written like this. It's a little bit simpler than the let form because there's just one sub-expression, so there's nothing to be confused about. And so if I've got some lambda x dot e, so that's a function binding the x, I could always rename that to a y by, well, saying y. Let's bind y now. And what do we have to do here? We've got to replace references of x with references of y. And we saw that with substitution. And just to be clear, right, substitution, I could hypothetically plug any expression in for a variable. And one of the expressions is just another variable. Right, that's a special case or instance of substitution. And so this says I can always rename x for y by replacing x with y. And then there's that same side condition that it can't be the case that y is in the free variables of e, because that would cause capture. So all these same issues of capture avoiding substitution, free variables, yada, yada, is really the same thing as what we did in that little language with let binders. So I could go over the definitions of these things. What is the definition of substitution? What's the definition of free variables? But we went a little bit over on time before, so I'm going to skip that for now because that's done over and over in hundreds of textbooks and papers everywhere. So that's easy to find. If you have a question about that, you can come to me after. Yeah?
Just a quick question since we're detailed about the syntax.
Yeah.
You guys have, like, you write your expression first and the substitution after.
Oh, sorry. Do I do it the opposite of Jan?
Yeah, is there like
They mean the same thing.
a right way? I mean, I'm sure it's biased.
People do different things. Yeah, I don't know about right. So people also do different things in the slash. The main thing is to be clear. So I'm so used to writing it, I didn't even notice, honestly, looking at Jan's stuff, because you do get used to reading it either way.
Yeah.
But yeah, I mean, this is the thing being substituted into. This is the variable being replaced, and that's the replacement. When I write it. Yeah, it's the same thing, though. I suppose somebody probably believes that one's right and one's wrong. But, I mean, it's the information content. And the way that you present the information content is less important. Yeah. OK, that's a good question. All right, so that's the, so that's the first one, right, alpha. And that's why it's called alpha, because it was the first. And it's what you need to just get going to even be able to read the term successfully. All right? So what's the next rule? The next rule is beta, because that's the second letter of the Greek alphabet. And what's the beta rule about? That's what does function application do? What does it mean to apply a function to some argument? And if you've taken high school algebra or calculus, you might remember that when you were faced with some function and you apply it to an argument, what do? Well, you just plug it in and go, right? That's all you're really doing. And so that's all we do here. If I've got a function, which here is represented in line, so instead of saying f of x, where f is defined somewhere else as something, right? Here, the function is itself a term that you can apply directly rather than by giving it a name first. And so if I have a function, lambda x dot e, I apply it to some argument, and I'll write the alpha there just to be clear, some e prime. What happens? The beta law says that you plug in e prime for x inside of the body of the function e. So this is e with e prime for x. And if you remember the dynamics that Jan gave for let, it's kind of similar, right? What do you do for the let rule? You plug in the binding of x and do a substitution. It's basically the same thing, but we do it across two syntax nodes instead of just all in one. Okay? So that's the beta rule. And then the last rule, the last law of what the lambda calculus is about is, as you might guess, the eta law, because we're going to skip a bunch of letters for some reason. And so what's the eta law? So this one's just about what static scope is. That's the first law. It told us what a programming language should do to implement static scope. This one is how do you implement a function call. And the eta law is kind of the other way around. This says if I've got a function and I apply the function, what's that do? And the eta law is that if I've got an application, a generic application, and I abstract over that, what does that do, or what can't it do? Right? So here it's a lambda applied to something, and or rather an application of a lambda, and here is going to be a lambda of a particular sort of application, which looks like this, e applied to x. So let's read this term. What's this say? It starts with a lambda, so it's a function. X is the parameter, or the argument of the function. And what do we do if we have an argument x? Well, we just call e. So what's this function going to do? I mean, it's the same thing as e. They say you give me an argument and I call e, right? I'm just delegating all responsibility to some subordinate, and I don't do any work myself. So you might as well just say that I'm the same thing as my subordinate, because I'm not adding anything to the picture here, right? And so that eta law says that this delegation kind of wrapper function is the same thing as the underlying e. It's not adding or changing anything from what we had to begin with. Are we happy with that? Is anyone unhappy with that? Somewhat unhappy? So there's a few reasons why you might be unhappy. There's one reason I'm really unhappy, which is, what if x is a free variable of e? Oh, these stupid free variable side conditions. Static scope is a pain, but it's worth it. So you want to make sure that x is not a free variable of e, because then this would be a capture kind of scenario, right? E might point to something in its environment, and this would say, aha, I've captured that e. So, I've captured that x, right? If e points to x, it should still be able to point to x, and this would get in the way. So usual kind of, whenever you add or remove a binder from something, if you're not doing a substitution, you should check that you're not capturing a free variable, and if you are, you're probably doing it wrong. Is kind of the intuition of just be very, very careful that that's what you mean, right? So here we're deleting a binder without plugging anything in, so you have to check that. All right, so any questions about this so far? We good? Okay. So these were just laws, but they don't exactly tell me how to run a program, right? So a programming language is more than just some syntax and then some of these kind of abstract equations. I want to know that if you give me an expression, program, I should be able to figure out the answer. And how did we see that, right? That was with the dynamic semantics, where it's some sort of transition system, right? A bunch of transitions or simplifications that will incrementally get me to an answer, right? How do we define the dynamic semantics of the lambda calculus? And we're actually pretty close to having it, right? So that beta rule telling me what a application does, that's really the computational engine of the lambda calculus. It's what drives it forward. And it's how it tells me how to simplify a program to get an answer, right? When I have a function, if I give it an argument, this is how you get the answer, and at least one step closer to the answer. So to get the operational semantics, we just have to say, how do you apply that kind of transition to an expression? Okay? So pretty, not too different than our little language, really. It's just a lot smaller, so there's less cases and rules to deal with. So that's going to be the primary transition, the axiom of the system. So, and the only thing you really have to say is which direction do you go, right? Do I go from the right to the left, or do I go from the left to the right? So who votes for right to left? Do I take some substitution and then give it a name? No, that doesn't really make a lot of sense. Clearly, I'm supposed to go left to right, and that's why it's written that order already. So I just have to commit. And so this is the main rule of the transition system, right? So if I have, if I've got lambda x dot e, and I apply it to an e prime, then that transitions to e with e prime for x. Okay, so that's the main rule of the system. Am I done? All right? Does anyone think I'm done? Does anyone think that there's something more I have to say for my transition system? Do you remember what that was? What else do I have to say? So what happens if I don't just have an application of a function? Right? So what if I have, for now I'll just use numbers as an example, but what if I've got lambda x, lambda y, x applied to 1 and applied to 2? Write the parentheses explicitly. Does that rule apply? So it doesn't apply, directly at least, because this doesn't look like an application of a lambda. It's an application on top of another application. If you were to write out this syntax tree, it would look like app to app 1, and then this is going to be a lambda x dot e. Right, something like that. So that rule says if I've got an app of some e, and then I've got a lambda x e prime, then I can transition to e prime, the tree e prime, where I've now replaced e. Every time I had an x, that instead now points to the tree E. That's sort of pictorially what's going on. Substitution is just traversing through this big long tree and replacing certain instances of X with E here. Does that make sense? So this rule does not match this tree directly because this is not an app in a lambda. Right? Really, I want to say, apply that rule here. That would be fine, and that would make sense, right? So that's why you needed these extra rules which say, okay, fine. If you don't have a program that looks exactly like this, this is where you go to look for something to do. Does that make sense? Those were those extra rules of, well, if I've got a plus of two things and they're not numbers yet, you go and reduce one or the other depending on the order. And so you need that extra rule here, which says that if I've got some E1 applied to an E2, and well, maybe that's not a lambda right now, but maybe I can take a step to get it closer to a lambda, right? So what if I've got 1, and that takes a step to E1 prime? What if I've got that? Well, then I can reduce this by just reducing E1. And kind of ignoring E2 for now, and it's just along for the ride. I'm just waiting until I actually get a lambda so I can apply that above rule. Right, so this takes a step to E1 prime applied to E2. OK? Good? And so this definition is the call by name version, I remember. So we saw in the previous lecture call by name and call by value. I did call by name first. And that's because I just substitute whatever the heck arbitrary expression for a variable. I don't worry about evaluating it first. OK? And so this, because there's not much going on in this little tiny language, this is enough to define the dynamic semantics, right? So this is a call by name semantics for call by name. This is sometimes called an operational semantics for the lambda calculus. That's all you need, right? And it's pretty small because the language is very tiny. I also wanted to mention, OK, so first, what happens in this term? Can we actually reduce this, right? And so the reason we can reduce this is because we've got that extra rule, right? So we now have the rule that says we can apply within the function part of an application first. So that would be this part here. And does this take a step? Can we tell if that takes a step? Right? So this matches exactly this form, where the E is lambda y dot x, and the E prime is 1. Right? So because lambda x dot lambda y dot x applied to 1, because that can take a step somewhere. Where does this take a step to if we apply that rule? We sort of looked at substitution. What's the right-hand side here? Can anyone tell me? Yep. Yep, lambda y dot 1. So we just plug in 1 for x, and x is used right there. Right? So this goes to lambda y dot 1. Right? So that means this whole thing goes to lambda y dot 1 applied to 2. Good? So we can make progress. And now here, OK, that's easy. I can just apply that rule. So shortcutting, what happens when I plug in 2 for y? What do I get? I get 1. Right? So now I can apply multiple steps. I can apply them in the correct sub-expression when it's not completely obvious, and I can get to an answer. OK, good. And want to write the shorthand that is very common that people use all the time in papers, if you read these, which is, so here it's not so bad, this one extra rule. I just have one extra little inference rule that tells me how to move the reduction step into a subterm. But when you have larger languages, like even E, it kind of gets tedious with all these extra rules you need. This isn't so bad. So one way of simplifying this idea is to essentially define the context in which these rules apply. So instead of saying, here are all the rules for lifting a single step, you'd say, here are all the contexts where you can apply a step. And they mean the same thing, it's just a different notation. And when you use the common conventions, the other one can be much simpler. So for here, what are the contexts in which I can apply the rule? So it's commonly, the notation is to say E, capital E for evaluation context. So the evaluation contexts, what are these things? They are expressions with a hole in them. And I'm going to write the hole as a box, and you can kind of think of this as like a special sort of variable. It's a little bit different than a regular variable. But this is, right, if you think of context when just reading, I've got an entire page, and then I want to look at a single word or a sentence. That appears in the context of a page, and you could highlight or put a box around the sentence or word you're interested in, and the rest of it is the context. So here, this is where the person of interest or the expression of interest is situated, and then the context is everything around it. So what are the contexts in which I could reduce? So here, if I've got an application, I can reduce in the function part. So I could just reduce an expression immediately, or I could reduce it inside of the function part, which looks like this. Right? So an evaluation context either is just a whole, which is to say the whole expression is what you're reducing, or it's something inside of the function part. And then this lifting rule here can be written as instead, if E reduces to E prime, then E inside of some evaluation context reduces to E prime inside of that same evaluation context. And so we should also define what do these square brackets mean. And it's really similar to substitution. Right? We want to basically plug in something for that box. Okay? So let's write it really quickly there. If I've got a box, and I'm plugging in an E, what's that equal to? Any questions? So if my context is, well, there is no context, and the person of interest is the whole expression, what should that be? This is kind of like the variable case. I want to replace the box, so that's just going to be an E. And then the only other case is what happens if I've got something that looks like this. An evaluation context, and then some E prime. Well, if I want to plug into that, what's this look like? Any guesses? So I can't plug in a term into another term, because a term doesn't have a hole in it, or an expression doesn't have a hole in it, but an evaluation context does. So kind of the only thing I could do to recover an expression out of this is to plug little e into big E. And I shouldn't throw that out. I should keep the context and just push this in. So that is E, big E with little e in place of the hole in it, of the square. And then that's applied to E prime. Okay? So here there's not a lot of savings. Usually you wouldn't write this down. It's sort of implied that if I've got evaluation context, I mean I can apply these rules and in any of these evaluation contexts. But when you start having more, the savings add up, because these are pretty short to write, but an entire inference rule gets long. But they mean the same thing. A question? Yeah.
Is there some description of what is a well-formed term?
Everything.
You want to need to can't just be anything X.
Sure. Yeah, they can both be X. This is a well-formed term. That's a term. That's an expression. Have to reduce. Not every expression reduces. Yeah, it is an application. So this doesn't say that every, so here I'm not saying that every syntactically well-defined expression reduces or gets to an answer. Sort of see several ways that happen. So one of them is, what if I get stuck on a free variable? Then you might say something about closed. Although that restriction of being closed kind of gets in the way because I don't have any other constants like numbers. So maybe you add in constants if you care about being closed. But in general, the idea is, at least for now, anything you can write with this grammar is a valid lambda calculus expression. It just might not have the properties you want yet. And we're going to talk about how to get some of those good properties back. But yeah, so it is very simple. But I'm not making any restrictions yet.
One point just now in this discussion is
Yep.
this can't apply a term to a term.
You can't apply, so this was a plug-in operation. So this is an operation on top of, evaluation contexts. Right, so I'm defining, so this isn't syntax. This is an operation. I'm manipulating expressions in evaluation context to generate a new expression. The meta-level type of, is it an expr or is it an eval context, right? So there's typing at that very high level, meta level, but not much more than that right now, right? So these are just different sets in my world of mathematics and purity, so I can tell that apart. But I haven't done, this function application makes sense inside of my programming language. That's a step next that you have to be a bit explicit about. Okay, so, all right, good. Yeah?
Specifying this is call by name.
Yes.
I thought the call by name didn't need the seconds.
You do for that. So we'll see, I'm going to do call by value in a second. So call by name still needs evaluation context because these actual reductions or transitions, they don't apply to very many expressions. And most programs wouldn't go anywhere. So you still have to say how to find where to do the reduction. The difference is, do you pre-evaluate an argument?
So for
the difference.
It's that your order matters. It's that you're trying to substitute first, and then if you're stuck, then look in the context.
Something like that, right? So here I'm substituting the argument without even touching it. That's the hallmark of call by name, that you substitute before evaluation. Call by value, you evaluate before substituting. Right, so that's the big difference. And call by name is kind of an awful term, but it's what we're stuck with. By name doesn't mean a lot, but at least call by value means something. And the whole point of call by value is I don't do the function call until I've got a value. And a value is not every term, or not every expression, right? Only some expressions are values, like a number would be a value. But an application probably shouldn't be a value because I don't know what it is yet, right? There's that difference between I've got an application versus here's the results. Right? They've got something to do, so they're not values. So now let's look at call by value and how we do that. So what's the difference between call by name and call by value? So call by value. Luckily, the lambda calculus is small, so these definitions are very short, which is nice. Okay, so call by value, what's the difference? The difference is the beta law doesn't always hold. I only want to substitute when I've got a value. That's really the motivation of call by value. It's what most programming languages do, and we want to model that within our semantics for programs. So here, the idea is, if I've got an application, then I can only do the application when I've got a value. Or I can only resolve the function call when I've got a value. So that's going to be E with V for X, right? Same basic idea, except I'm willing to substitute. I didn't really say that yet. I didn't say what does V stand for. So V should stand for a value. And what makes a good value? I'm going to say that a value is everything that's not an application, right? So a value might be a variable, or it is a lambda. Those both could be values. It's a value because it's the sort of how you define a function value, a function pointer or reference, right? You could think, I have defined in C or Java, oh, there's some function named f with a parameter x and result e, and now I'm referring to f. So here it's that first class for a function, and I'm also allowing variables x. Okay, are we happy with that? Variable, and there's some choice to be made. So in some sense, you might not want to consider variables because you only want to talk about closed stuff. And a variable, it's got at least one free variable itself. Maybe that's a problem for you. On the other, a variable stand for, right? It's an unknown quantity. What kind of quantity? Well, it could only be a value, right? I'm only ever going to plug a value in for it. It's not some other weird bogus thing. X has to be a value at the end of the day. So it's not wrong to call it a value if you're in a situation where you don't mind free variables. So the original definition of the call by value lambda calculus used this definition. Everything as just that, just lambda values. Things like numbers and so this rule now means something, because I've said what V is. We're not done, right? That looks like this. That would be convenient if that was always the case. But right, so how do I find all the expressions that are reducible so that I can keep applying these rules and get you an answer? All right, so let's get started. And to begin with, context. So the context, the call by value evaluation context. So in comparison, one way you can think of call by name is I want to apply rules in the still get it. Right, so in general, this has got to be turned into a lambda for me to ever get anywhere. So I've got to evaluate E1. Do I evaluate E2? Clearly, that's a choice I make based on my own preferences. So if I don't at least include the same evaluation context as call by name, I'm going to get stuck in places that I shouldn't. So evaluation contexts are the empty context, the box, or an evaluation context applied to some argument. All right? And what else? Is that enough? Are we good? Do we have any hints that I'm done or maybe I'm not done? So, what was that? We need one more. Right? I'm only allowed to actually do this when my argument is a value. What if it's not a value? I can't do anything. So I probably should try to evaluate the argument to at least attempt to get it to a value before getting stuck. So there's one more case of the evaluation context, which is to say, once I've figured out a function that belongs here, I should then move on to work on the argument. Right? So figure out my function pointer, figure out my argument. Once those are both evaluated, then I can apply this rule. And so that extra context looks like this. VE, right? So if that's already a value, then start evaluating the argument. And note, yeah, so that's how you would present. And this is a pretty common way of defining call by value lambda calculus. You say, this is the reduction rule that matters. Here's my definition of value written in BNF, and here's my definition of evaluation context, also written in a BNF. Okay? And just to sort of finish off over here, there's one more case of an evaluation context. So can anyone tell me how I should finish this definition for call by value? All right, because I'm not done yet. What happens if I've got that new case? So what if I've got a V applied to a big evaluation context E? Where do I stick my expression? Yeah? On the big E, right? That's kind of really the only place I could put it. So this is just V applied to big E, and you plug in the little e for the whole. All right? And so the reason why this is convenient is because this definition is fairly straightforward. I mean, it pretty much is the notion of substitution. And, well, yes, of course, you apply these rules inside of an evaluation context. So if E steps to E prime, then E inside of an evaluation context steps to E prime inside of that same evaluation context. So this part is predictable and by rote, and you often don't even bother writing. This part you often don't even bother writing, but if you want to be really formal, you might want to, and then this is sort of what you need to define the rest. Okay? For comparison's sake, I'll write the inference rule style that we saw last time, just to sort of go the other way. First I started with inference rules, then I wrote evaluation context. Now I'm going the other way. I started with an evaluation context definition. How do you expand that into inference rules, which are more general but more verbose? Right, so how do we do that? We have two judgments, right, or really two things, which was how do I know what's the value, and how do I lift reduction into sub-expressions? So what's a value, right? So x is a value, right? That was one of the things. What's a value? That's how I wrote it before. And then what else? Well, lambda x dot e is a value with no other assumptions. Those are just both values. Okay? And then how do I write that rule? You can then write that as, so if e prime is a value, then lambda x dot e applied to e prime steps to e with e prime for x. Right? So that's another way of writing that same rule, where instead of writing V as a grammar, I'm writing them with rules. Everyone understand that? And then how about the rules here? Right? So this inference rule implies two other reduction rules, because there's two interesting cases of evaluation contexts. So what are those? So those are going to look like evaluate this part. If I've got some sort of application E1 applied to E2, if I can evaluate E1, then go ahead and do that. So if E1 can take a step into E1 prime, then the application can take a step into E1 prime, E2. But that's not enough, for call by value at least, because I still have to work on the argument 2 before I am allowed to apply this. So the other inference rule that's implied by this general one is that, well, if this part's already a value, I should work on that if possible. So if I've got an E1 applied to an E2, and E1 is already a value, but E2 could take a step to an E2 prime, then this takes a step to E1 applied to E2 prime. All right. So that's, and these two definitions are the same. Right? There's no real different informational content. It's just a different style. And sometimes you might see one or sometimes the other And it's useful to have these multiple ways of looking at it to get a better understanding of what's going on. All right. So, let's look at some more examples. Are there any questions about the operational semantics? It's almost simpler than what before because there's fewer cases. But it's a little more general somehow. And I'm going to look at briefly how. So it doesn't seem like there's much here. Right? Before we at least had Booleans. And there's no Booleans. So how can you do anything? Right? There's also no numbers. But if there's no Booleans, I don't really have a programming language. So what's the point? Right? This seems pretty boring. So let's look at how you can fake it if that's all you've got. Right? So this is, lambda calculus faking it with style. What are the constructs, the programming constructs for Booleans, right? You've got the two Boolean values, true and false. You've got an if then else. That's sort of the very general operation. That given a Boolean, I can do whatever I want based on which of the two things it is. So I should have a way of defining if E, then E1, else E2. That's how I use a Boolean. And then how I is with the constants true and false. OK. So I have to find a way to represent these things without actually having them. All right. So that's the game I'm going to play. This is the encoding game, which is a very fun game to play, which is how do I make do when all I've got is function abstraction and application? OK. I get to pick where I start. And I'm going to start. So I've got to do three things. If then else seems hard. It seems fairly hard, actually, right? How do I make a decision and do an if then else? OK, well, since that's hard, I'm going to make it easy on myself and do the stupidest thing I possibly could. So E makes the decision. So I'm just going to say if then else is going to mean, so I'm going to say that this is a macro which expands into a lambda calculus expression, right? So this is not syntax in my language, but a syntactic sugar. And that's going to be E applied to E1 and E2. Write the parentheses. So usually when parentheses aren't written, it means associate to the left like that. Certainly I've got each sub-expression in there somewhere, and I hope that somehow this makes sense. So I'm not wrong yet, because I haven't said what true and false are. So if then else is this, how can I arrange a definition for true and false so that this actually does the correct thing and instead of something bogus? Right, so that's the idea of at least one way to approach the encoding game is find the hard part, make that stupidly easy, and then make everything else work with that. So if an if then else is nothing more than a function application where I provide two arguments, first the then branch, then the else branch, how do I define a term for true and false so that this does the right thing based on our operational semantics from before? So I'll say something for true, right? So this is clearly two arguments. I apply one thing and then another, so there's got to be two lambdas for this to make any sense. Got a lambda x and a lambda y. And what should be the result if I pass in the then branch and the else branch? It should be x, right? It should be the then branch, because clearly if then else on true should be E1, and that's x. Great. When I've got if true, then E1 else E2, then that will reduce in many steps to E1. And that's great. That's exactly what I need, right? That's all I need out of if then else. Perfect. All right, so what about false? What should I write here? So again, two lambdas, right? It's two functions. Lambda x, not lambda y. And now what is the result? Y. Perfect. And so if false, then E1 else E2 will go to E2. Perfect. I have now defined Booleans. I had no Booleans. Right? So that's kind of the magic trick of the lambda calculus, is you can define all these other programming constructs when you didn't have them. And that's one reason why it's deceptively powerful. I've got Booleans even though I didn't have Booleans. And in general, the lesson is that when you're defining these programming language things, it's surprisingly easy to wind up with way more than what you intended to put in them. And we're going to look at that in a moment now. Let's look at another example. Are there any questions about that encoding? So let me see. I'll write an extra homework assignment because clearly you don't have enough yet. But this one's a fun puzzle. And you can find the answer online, so I would suggest trying it out yourself before you spoil it. But this may take you a little while to figure out, is encode the natural numbers. So it's numbers greater than or equal to 0 in the lambda calculus. Right? So it's just like Booleans, you just have an infinite number of them is all. So that's a fun one because it's a lot more advanced, but to sort of see these encoding tricks. And so don't be frustrated if you don't get the answer right away. But it's fun to think about if you can kind of figure out what is. And so same thing I would say, and it's why it's a little bit harder. Here I said, what's the main operation on Booleans? It's if then else, clearly. And I said, make that easy. So that one of the tricky parts is what is the main operation on numbers? And figure out what your main operation is going to be. And then define everything else to go along with it. OK. So there's a homework. Let's look at another example in the encoding game. So I'm going to define some representation of sets. Right? And so what are sets? What is the primary observation on a set? Really the only operation is membership, in the most basic sense, right? Is something an element of a set? Right? And so same thing, I'm going to make that easy, and I'll say I will define set membership. E is an element of E prime by asking E prime, is E in U? And that is just going to be function application. So that's your Rosetta Stone for sets. And now I'm going to look at, well, so let's look at a couple examples on how you would use this to define some basic set operations. So what about union? So I've got E1 union E2. How would I write that? So a union says for any element, if you ask if you're in a union, it is if it's in either. Right? So you could do that with an or, right? So this returns a Boolean is the idea. So if you ask me if X is in the union of E1 and E2, I will say yes if it's in either of the two. And so that's with or E1x, E2x. And I'm not saying how to define or, which is another thing, is encode or using the Booleans. But clearly, if you've got Booleans and if then else, you can write or. So that's a union. What about an intersection? So an intersection, some element x is in an intersection if it's in both. So how do you write that with just Booleans? Right? It's not an or. What is it? It's an and, right? So if you are in E1 of x and E2 of x, then you are in the intersection of E1 and E2. Okay, good. So we can also have sets. So we can kind of see we've got more than what meets the eye. But now let's look at a really fun example, which is Russell's paradox. So who here is familiar with Russell's paradox? Okay, maybe about half of the people. And so this is a fun paradox in set theory, which is Russell defined a set, which is the, so Russell's set is R, which is the set of all sets that do not contain themselves, right? So you would write this using set notation. So it's the set of all sets E such that E is not in E. So if I write that, okay, fine. So do we understand what's being said there? Is the set notation at least clear? I want the set of all sets such that that holds, which is to say E is not in E. Okay, and then Russell asked a question. Is R in R? Who thinks R is in R? Who thinks R is not in R? Who thinks that this is totally bogus? Okay, right? Because if R is in R, well, then it couldn't be in R because R is in R. So, okay, well, it must have been that R isn't in R, but then it ought to be in R because it includes everything not in itself, right? So this is the paradox that if you define such an R, then you can ask bogus questions that don't have an answer. It's not just that I don't know what the answer is, it's none of the answers make sense. Okay, so what happens when you use that encoding over there? So how do you define R using lambda terms? R, well, set that if you ask it if some x, which is another set, is in R, when do you say yes? You say yes when, well, ask x if it's in itself, ask if x is in x, and then say whatever the opposite of that is. So x is in R when x is not in x. Okay? So it's just writing this in that lambda calculus notation that I wrote the key code over there. Okay? So now what does this question mean, right? R in R is encoded as R applied to R. All right? So what does that mean? Well, we've got these reduction rules, right? Or I can just apply beta left to right. That's what the program means. So what happens if I apply the beta rule here? Because this is R, it's lambda applied to something. So that takes a step to this, where I plug in R for x. So that takes a step to not x applied to x, where now I'm going to replace R for x. What is that? That is not, the definition of substitution says this is not R applied to R. So it's not whatever I asked to begin with, but oh, I can, let's say I'm in call by value, I can try to evaluate that, right? So where does that go? Well, what happens when I apply R to R? I get not R and R, right? So that steps not R applied to R, and that steps again, right? So I could keep going, and if I keep going, then I get not of not of not of not of not of not forever. So that means that in this little language, it's not just the case that I could get stuck on weird things like that. I could loop forever hopelessly. So the paradox in mathematics shows up in the lambda calculus because I can write it just fine. But when I try to find the answer, I end up spinning forever, and I don't make any progress. Because there's a difference between a question and the result. Just because I could hypothetically try to find the answer doesn't mean I've got one. Okay? So, yeah. So here's another thing you've got that maybe you didn't want. So if I just had the little language with like numbers and addition, clearly those can't go on forever, at least the addition part and the equality part, because each step makes the term smaller. And even the let doesn't cause a problem. But somehow the lambda and the application added a new feature to my language that add, which was looping forever. Okay. And the simplest case of this is sometimes written like this. Is even simpler. Right? It's a self-application of a self-application, which is kind of similar to the Russell's paradox, but I removed the not part. And what's the point is that omega steps to omega again, right? It's not even that you expand, you just take a step to get nowhere, right? So clearly we've got infinite loops. So that's kind of not a good thing. But maybe it's a good thing, right? I don't really want to spin forever because that's pointless. But you can take advantage of this. So why is this bogus? Because the infinite negation of a Boolean doesn't really give me an answer. But maybe if I keep composing some other sort of function, that could be useful, right? So what if instead of Russell, where I take the negation of a self-application, what if instead I do this? I'll call it y of f is equal to lambda x, f of x applied to x, lambda x, f of x applied to x. All right, so this is just like my question is r and r. Now instead of not, it's where. And so what happens when I try to reduce this? What does y applied to f step to? It steps to f of y applied to f. So this is called the y combinator, because why not? And who's seen this before? So some people, so if you ever forget what the definition for the y combinator is, just remember Russell's paradox, and there you go. Make that useful. But why is this useful? Right, so this, the idea is that this is a fixed point. Y of f somehow is an expression such that it is the same thing as f of y of f, right? This is an idea in mathematics, right? I could have some point on a grid where if I apply some function f to it, the point doesn't move. That's why it's called a fixed point. And why are fixed points useful is because you can use that to implement recursion, right? So you can implement a loop using a fixed point. So let's look at a simple definition. So how do I write times multiplication in terms of addition? Right, so no trick question. It's if I want to write times, and I'll use the syntax of the Lambda-Calculus for functions and applications, but let's just assume I have all the number stuff from before. So I've got addition, I've got comparison. So how do I do that? Well, multiplication is a function of 2 arguments. But you write that, 2 lambdas, because I can apply twice. And so how do I define times? Well, you can do it by checking x, right? It's by induction on x. If x is less than or equal to 0, then what is x times y? So for now, just assume, even here, let's assume it's equal to 0 and forget the less than part. 0 times y, that's 0. OK. Else, it's something else, right? And so how do I simplify that down? Well, I could, right? I know the previous case when x is 1 smaller. And so that's going to be y plus times x minus 1 and y. And so let's convince ourselves that this does make sense. It's just some other notation for functions, but it's not that different than you'd write in a language or mathematics. OK? But this isn't really a macro definition in the Lambda-Calculus. I can't write this in the Lambda-Calculus because the left-hand side appears on the right-hand side, which means to expand it, I've got it again, which I'd have to expand again. And so this, as written is like an infinite term, or somehow I've got a recursive equality in my language that's something else. But the trick is to abstract over the recursive call to times and passing it in as another argument, and using then y to close that loop. So how do you do one step of times, and then how do you close the loop is going to be with y. So times-ish is the first argument is going to be the function for the next step. And then I'm going to get x and y. And then I'm going to pretty much do the same thing. So check, is x 0? And give back 0. Else, do y, y plus, well, x minus 1 and y. And the whole point is don't talk about the thing you're defining again. Just say do the next step. Oops, do the next step, whatever that happens to be. I don't know, but this is now a sensible definition of times-ish. It's kind of like times, but I need this extra argument to tell me what to do next. And then times, what's that? We'll find the fixed point of times-ish. The thing where every single time you do times-ish, right? That argument next should just be do this over again. And keep doing the same thing over again until you hit the base case, where x is 0. So times is going to be y of times-ish. Times-ish. OK, good. So another good homework exercise. Convince yourself that this actually means times. Right? I wrote it, but I didn't prove that it's the real deal. But the point is, because we've got this paradox in the language, you can make that a useful thing for doing stuff, which is recursion, which is another thing the lambda calculus didn't have and yet did anyway. Right? I didn't add a recursive construct or any sort of self-naming, and here we go, we've got one. Right? So it's got a lot more stuff than what it lets on. OK. So there's not much time left, but I do want to wrap up with the final thing. So here I just talked so far about the dynamics, right? The dynamic semantics, how programs move. But I didn't say which programs were good, right? Which programs had that kind of type safety thing or doesn't try to do bogus stuff. So what is the type system? Giving me a static semantics for the lambda calculus. So people refer to that as the untyped lambda calculus because you say, every expression is fine, just go ahead. And if you get stuck, it's your fault. Don't do that. But you can still add types to it, which prevent a lot of bad things, like maybe x applied to x, which gets stuck, or things like that. And so let's look at those. So what are the types of the lambda calculus? So we've got to write those inference rules for the same sorts of judgments or hypothetical because we've got free variables. So there's a gamma, an expression, and a type, just like before. And so what are the rules? So one of them is what happens if I've got a free variable? What's the type of a free variable? Well, I don't know. It could be anything. Where do I find that from? That environment thing. If I assume x has type tau, then x has type tau. Oh, I should actually write down what are the types. So what's the types of the lambda calculus? So yeah, what are the types? OK, so clearly I've got functions which are normally written as an arrow. So tau1 arrow tau2 is a function from some input type to tau1 to some output type tau2. Is that good? We're shrugging. So that's really the only thing. Is there any problem here, though? Anyone know if there's a problem? What's the problem?
Functions are from type to type, but this type can only be function. So this
Yeah.
makes it up being degenerate.
Right. So there's no base case. right? And it's not even a sort of, well, I'd like something useful like a number. I really just can't write down a finite type if that's all the rules, because every time I see a tau, there needs to be another arrow forever and ever. So, OK, fine. I'll write here alpha, which is going to be some sort of constant, which I'm going to leave vague. But the idea here is that alpha might be a useful thing, like a number or a string. I'm not really giving a real semantics to it, but it's a placeholder. So with this definition, OK, now I can have types like alpha arrow alpha. And that makes sense. That's a type.
So you really have a family for simply Lambda-Calculus.
Yeah. So there's different ways to look at it. Some of the ways are that I've got a family where this denotes a particular set. I could say that this is sort of the initial model, where you can just say that these are undefined variables in any particular choice. It's one of those. And that's kind of usually what it is. These are left unspecified, and we don't get more specific than that. But when you start adding in real constants like numbers, Boolean strings, or many other things, then you don't have to sort of be abstract about what does that alpha stand for. Great. But then that was getting back to the typing rules. So that was one of the typing rules. The type of a variable is what I said it is. Right? It's typing by fiat. OK, and then what else? So let's do an application next. So what is the type of E applied to E prime? So what should E be? E should be a function, because this is a function application, and that's the function part. OK. And a function is some sort of arrow thing, so I'll just write tau prime to tau. That's some sort of function of an input type tau prime and an output type tau. And then if that's the case, what should the type of the argument be, at least intuitively? It should be tau prime, right? That is the input. So the type of the argument should be the type of the input. So E prime should have type tau prime. And if that is true, so yes, this type checks, and specifically at what type, right? This is well typed, and the type is tau, which is the type of the output, because when I apply a function to an input, I get the output, which has that type. OK? And this, if you want to give a name to these rules, you could call this arrow elimination, because I had an arrow and I used it up. So it's elimination because I had one above the line, it's gone below the line, right? OK. And one more thing, right? This is a nice small language, so the inductive definition is almost done already. So the last case is what happens if I've got a lambda. What should the type of a lambda be? So a lambda is a function, and the function type has an arrow. So it should probably have an arrow. It shouldn't be something else weird like a number, because why would a lambda be a number?
Some tau arrow empty box.
Tau arrow empty box? What's an empty box?
From evaluation concepts.
Oh, I see. No, so there's no empty box in the grammar of types. I didn't put one in there. It's got to be 2 tau, so it could be an alpha, but it could also, I'll just say a tau prime, which is I take some input type, I transform it to an output type. This is a well-formed type, assuming that tau and tau prime are, which isn't that hard to imagine. And this makes sense because lambdas make functions, and that's the type of functions. OK? And so what's the premise? When is this the case? Well, the body of the lambda is the result. So it should probably have the result type. So E should have type tau prime, because E tells me what the result is, assuming I've got some input x. What's the type of that input x going to be? That's just the type of the input, right? So we should assume that x is some sort of tau coming in, and then check that the result E gives back some sort of tau prime. And then if you want to assign a name here, this is arrow or function introduction, because from top to bottom, I've made an arrow. Right, question? Here? So here, and this is the binding, right? Lambda binds the x. So x is free inside of E probably, right? And if you refer to x, it should be the tau. And here, x is bound. It's no longer free. And so we don't, right? So the idea, the interpretation is that gamma includes all of the free variables of this term here. Maybe some more that I'm not using in this case, right? There may be extra ones. But it has to include every free variable, or it doesn't make sense. And so here, we're allowed to not say x, because it's no longer a free variable by definition of the fact that lambda binds that x. So it couldn't be free. Yes, so this is, if I've got some big derivation tree up here, which told me this was the case, then this is safe to conclude. So here, you could annotate every binder with the type, and that's sometimes useful, but that's not necessary for defining this inference system inductively, because you're saying, assume that this already makes sense. If this makes sense, then certainly that makes sense, right? If I know, if I've got some big derivation here and some big derivation here, which tells me that E is a function of this type, and that the argument is a compatible input of that input type, then I can safely conclude that. A question? Was that? So not every expression is well typed. And we saw that before, right? If I add true and false, that wasn't well typed in our little language. Huh? Oh, is that well typed? Yeah, okay. So lambda x dot x. Well, what's the type? Let's say it's alpha arrow alpha. So let's build the typing derivation and no free variables, because there aren't any, so I shouldn't need any. Okay, what's the rule I can apply? So these rules are nice because there's something called syntax directed, which is for each individual case of syntax node, there's exactly one rule to apply. So I really don't have that many choices. If that's my conclusion, what rule could I possibly apply? I can only apply that, right? So, okay, fine. The rule says that now assume x has type alpha and prove that x has type alpha. That's the arrow intro rule. And can I prove that? Which is, can I draw the final line which says I'm done? Sure, I mean, that's just that rule. So there's the type that lambda x dot x is well typed. And
they're saying, I don't know, because I feel always that it's more than just a function. That's a family of functions.
It is a family of functions, so this isn't the only type you could assign it, right?
Yeah,
so.
Okay, I think that the identity was special and maybe not the best example because
Yeah.
it's always alpha.
But it could be something else. It could be alpha arrow beta to alpha arrow beta. That will also type check. So this same expression, you could say it has more than one type. And that makes sense. And there's a lot of systems that'll have that property, that an expression might not have a unique type. It might have multiple different types.
A function that extracts an element of a sequence. Where
Yeah.
type from sequence of t
Yeah.
to t.
Yeah. So the get me an element of, get me the first element, say.
But it says it's kind of expresses parametric polymorphism, which is kind of...
Yes. Yeah, you're going to want polymorphism because life polymorphism is painful and terrible. So yeah, we'll get there. Yeah, so here's one. That's the type system. And at least I want to mention before stopping very quickly that, right, so type systems, the static semantics throws out expressions as not being well typed. Right? There's some expressions, probably, that I can't build a derivation that says it has some type. And what kind of expressions do I throw out here? And the answer is, for this type system, in particular on the untyped Lambda-Calculus, I throw out all of that recursive stuff. The self-application doesn't make sense because if x has type alpha arrow alpha, then I can't apply it to x because it doesn't have type alpha, right? If I assume, right? I have to pick one or the other, and it can't be both. So I actually do throw out some programs. And a theorem that I plan to get back to for this topic is that is termination, right? So termination, which says if a term E is well typed at whatever type, it doesn't really matter, then there is an E prime such that E will reduce to E prime in many steps. E prime does not reduce to anything, so it's done. So this is not a trivial theorem. That's actually quite a serious property for a language to have, which is to say it's impossible to write an infinite loop, which means you can't write Russell's paradox in or omit type lambda calculus. It just doesn't work because that would go on forever, right? So we are throwing out terms, and we're not just throwing out some silly stuck terms and dumb stuff. We care about what we actually throw out a lot of things. We also throw out y because if you make f the identity function, then that's the same thing. So y in general is not definable. So you throw out all of this extra recursive stuff, which I didn't really put in the language in there, but I didn't really put in the language to begin with, but snuck in. And when I add types, it's a way of controlling what I've actually got. So the simply typed lambda calculus isn't really much more than just the function part. There's no recursion, no other weird stuff. It's just functions and application, and nothing else interesting can happen. So types are a way of really tightly controlling what you let into your language. So I think I'm going to stop it there because we're over time. And if there's any other questions, I can answer those now. All right?